This video is about learning how to use Newton's first law of motion to explain the motion of objects that we might see every day. Going back to Newton's first law, 5 components. Every object continues in a state of rest or of motion in a straight line at constant speed unless acted upon by an outside force. Should be able to identify in any kind of motion that we see which one of those 5 concepts, 5 components, is involved in that type of motion. So we're going to explain the different stations that we went through and a few other situations that might come up. The first station we're going to go over is the beaker and wax paper station, where we had the wax paper underneath the beaker. We yanked on the wax paper and we pulled the wax paper out from underneath the beaker without having the beaker move. And the beaker is an object at rest and it wants to remain at rest unless some other force acts on it. Since the only force is applied to the wax paper, there is no force applied to the beaker, so it is going to want to sit there forever and ever. If you do want to move the beaker, then you need to pull slowly on the wax paper, and when you do that, then there's enough friction between the paper and the beaker to pull the beaker along with the paper. So if you go slow enough, then the outside force of friction can now affect the motion of the beaker. There are a few other stations back in lab where objects were sitting at rest that wanted to stay at rest. The penny on top of the index card wanted to stay at rest. The blocks wanted to stay at rest. The cork on top of the hoop wanted to stay at rest. And the pennies on your elbow wanted to stay at rest. So those are all examples of objects at rest wanting to stay at rest. And they're going to stay at rest until some outside force makes them move. Okay, so as soon as we apply an outside force to whatever it is that was beneath those objects, then gravity, an outside force, can act on them. So when we flick the index card out from underneath the penny falls to the bottom of the beaker. And since gravity acts straight down, it falls straight down. Same thing happens on the blocks. When you knock out the bottom one, the top blocks fall straight down. When you flick the hoop out from underneath the cork falls straight down into the beaker, and the same thing happens with the pennies on your elbow. Here's an example of something you might see in everyday life. You put your cup of coffee or your hot chocolate up on the dashboard of the car, come to a stoplight, waiting for the light to turn green, and as soon as the light turns green, you floor it and you take off quickly. Now, assuming the dashboard is frictionless, what's going to happen to that cup of coffee? So since it's frictionless, there are no outside forces that are going to act on the cup of coffee, and the dashboard is just going to move out from underneath that cup, just like the wax paper moved out from underneath the beaker. So initially, while it's on top of the dashboard, it's going to remain in its initial position, and the dashboard is going to move out from underneath it. Once the dashboard is moved out from underneath it, it is no longer an object at rest wanting to stay at rest. Now there's an outside force of gravity that is going to pull it straight down and into your lap. So the cup of coffee doesn't ever actually move backwards. It actually stays in the same spot. It's the dashboard that moves forward. Falls as a result of gravity acting on it once the dashboard no longer can resist gravity. Now, if you start out slowly, or if you increase the amount of friction between the cup of coffee and the dashboard, then it's going to act like that beaker when we pulled the wax paper really slowly, and it's going to move with the dashboard. Before we went back into lab, we talked about this pellet being shot into this spiral tube, and we asked you which path we thought it would follow. Had about half the class say A and about half the class say B. Should be able to explain this now after having been through lab. Correct answer is B. That pellet is going to want to travel in a straight line unless some other object or force acts on it. So while it's in the tube, it's going to be acted on by the outside walls of the tube. Once it gets to the end of the tube, there are no other outside forces, and so it's going to continue in a straight line. Should have seen this back in lab with the marble going around the tray. Once it got to the edge of that tray, it didn't keep going in a circle, it actually went in a straight line. There was a question on the spin the can station that asks you what would happen if you let go of the can. What direction would the can travel in? It's a diagram of a stone on a string being held by hand. And at whatever point you release that stone is going to travel in a straight line from that point on. This is the same kind of thing that you see in the real world when people are driving on ice really fast out in their cars and they want to make a turn. Objects that are moving in a straight line want to continue to move in a straight line. So your car is going to continue to move in a straight line on that ice unless some other force acts on it. If you can't get enough friction between your tires and the road, or in this case, the lake, then it's going to continue to move in a straight line. The only way that you can get it to turn is if you can apply some outside force to it. So you need to slow down so that your wheels can adhere to the surface, get a little bit of grip, and you can use that friction to help turn the vehicle. So when you start driving, the slower you go, the more friction you're going to be able to get, and the easier it is going to be able to turn on those icy roads. So when we were doing the spin the can with the water in it, the water wants to travel in a straight line just like anything else does. So what was it about this station that didn't allow the water to travel in a straight line? And the answer is there has to be some kind of outside force that acts on it to prevent it from traveling in that straight line. In this case, that outside force is coming from the bottom of the can. On the aerodynamic drag race, we dropped a piece of paper and a piece of lead, and the piece of paper slowed down as it went through the air. So why doesn't that piece of paper continue to move at a constant speed? And the answer is that there must be an outside force that acts on it. In this case, it's the force of air resistance that acts on that piece of paper to change its speed, to slow it down. Once we apply that outside unbalanced force, it can't continue at a constant speed anymore. Similar answer to why a ball eventually stops rolling when it goes through the grass. It wants to travel at a constant speed, but it can't because there's an outside force of friction that acts on it to slow it down. Why would your head hit the windshield if you weren't wearing a seat belt? And again, just like all motion, this can be explained using the 5 components from Newton's first law of motion. So your head is an object that's in motion and it wants to continue in motion unless some other outside force acts on it. In this case, the seat belt does not apply an outside force, so you continue to move in a straight line after the car stops, and the outside force doesn't come until your head hits that windshield, or you go through that windshield and something outside of the car stops your motion. So no seatbelt means no outside force. You keep moving in a straight line at a constant speed until some other outside force that is going to hurt a lot more acts on you. The other question that we asked before we went back into the lab is what would happen in this scenario where that ball on the string gets cut by a razor blade. Which path will it follow? Will it follow A, B, or C? And again, class is about half divided on the B versus C. After doing lab, now you should know that the answer is B. And as soon as it's cut, it's going to travel in a straight line until some other force of gravity makes it curl down. The only way that it can go up in C is if some other outside force makes it go upward. And in this case, there is no outside force that's going to make it go up.